Hello everyone. Now we will start new chapter, chapter 14, energy methods, which is the last chapter in this course. Also a little bit long chapter if I want to compare with the previous chapters. First of all, also you have any experience about the energy or work principle. Also, we try to apply these principle to beam deflection or strength of material term. First of all, we start with what is the meaning of the work. You remember from the high school, also dynamic course, if you take or not, I don't know. And work is equal to force times distance. It's the force is constant, we can multiply by the total distance. But if the force can change with respect to distance, we have to represent the work as the by using this function, integration function, from 0 to x, the f times dx, like this. Also, maybe in spring force, maybe you remember that F is equal to K times X, like this. In spring force, I want to show my camera in here. Like the spring force is F is equal to K times X, therefore integration is F times dx. And I want to represent this work as U integrated in Kx dx. So 1 over 2 Kx squared is the integration of the spring constant. Maybe you remember from formula from high school. This is the definition why we are using the integration. This is a good explanation for that rule. Okay, what about our beam structures? In the bicycle, you remember that our body is moved, but in here, our body is not moved, can make a deflection, displacement. So what we can calculate with the displacement or say work by done force. For example, we have some kind of bar like this, and we have a applied force like F. After applying force, we have like the displacement like delta. So if I want to compare it to this formulation, delta is related to F. Therefore, when the F changes, delta changes. Therefore, I have to represent this formulation. F is equal to, the integration is equal to F times delta from 0 to, and for example, delta like this. So our formulation we can present to this formulation. So why I'm using integration? Because F is also changing with respect to the delta. So what is the relationship between the force and the displacement? You remember from the material course, if we accept our material as a linear elastic material. So our force and displacements have a like this curve. Maybe you remember from the strength of material, relationship between the force and actual displacement. For example, in tensile test, or sigma epsilon graph like this. So, but mostly we prefer talking about the structures in elastic case. So we represent using the Hooke law. So if our material is linear elastic, so we have like the Hooke law. After that, we can define the simple relationship between the sigma is equal to E times epsilon. So if I have a what about in is for the force, if I represent as a force also in displacement, therefore we have a constant relationship between the force and displacement. So this looks like a spring force. So if I want to apply our integral formulation like this, you remember in u is equal to integration. I want to define, symbolize the p instead of f times d delta, 0 to delta. So I want to say integrate k times delta times d delta. So after integration, I obtain 1 over 2 k delta squared. So, p is equal to, I say, to k times delta. Therefore, our formulation is equal to 1 over 2 p times delta. So, also, you can see in the graph, also geometrical meaning of the integration of the area under the graph. Therefore, and this looks like a triangle. Therefore, our formulation becomes p times delta divided by 2. So, what about this? This is the external energy. So, if I have an external force P, okay, if I want to measure energy occurred from the P, we apply it means that P times delta divided by 2. But also we have another energy because we have a conservation of energy principle or work principle. How we can calculate? This is external energy force done by external work done by force can be absorbed from the beam or our rod structures. So there is some kind of deformations or internal forces can generate it in the energy. And these are the absorbed. Also, these should be equal to, we also define is, we can call this energy as an internal energy. So how we can calculate the internal energy? You remember, I already defined the sigma epsilon curve. You remember, sigma epsilon, this is an infinitely small element, and also I say the constant relationship. So if the energy in small u, I want to, like the du, I want to represent it, du is equal to 1 over 2 sigma times epsilon. This is the, why I'm using du, because this is the infinitely small element. dx, dy, and dz. So, sorry, I don't want to use du. And in dv, like the volume I want. Therefore, I want to take the volume integrating dv. I'm sorry, I want to use the du. It's much more better. And du is equal to like the dv. So therefore, in integration, we can say 1 over 2 sigma times epsilon dv. So volume integration. This is the internal energy formulation. This is caused from the normal force by shear force. Our stress notations just only change. 1 over 2 remaining. I want to use tau instead of sigma. Also, I want to use gamma instead of epsilon. Also, this is the internal energy absorbed from the shear deformation or shear force, shear direction. You don't need to memorize this, but I hope you understand the main theory. Force times displacement divided by 2. This is from the infinitely small element. If I want to integrate this infinitely small element for volume integration, I will obtain the total energy. So in our formulation, external energy and internal energy should be equal. Therefore, we can say U external energy should be equal to U internal energy. So, if we can measure, so we already know the P in the formulation. Also, we can compute the internal energy. And by using this relationship, we can use the displacement. You remember that, so we can find displacement. So why we are using the energy methods? First of all, by using energy methods, we can use the displacement of the body or deformation shape of the body by using this energy principle, by using this principle. Therefore, the main reason using this method in the work and energy principle. So I said to P is we know, delta is okay, we want, but we don't know the U. I said the U is I write to general formulation in here, but I want to go in detail what is the strain energy, and I want to divide the strain energy by using different effects, internal effects. First internal effects is axial load, because each internal effects we have a different formulation, different force stress relationship. Therefore, the internal energy formulations can be changed from bending, axial load, and shear force, also torsion. Remember, so how many internal effects we have? We have 4 internal effects. First one is the axial load. The second one, the bending. Third one, the shear. Fourth one, the torsion. Mostly shear energy and torsion energy is not extremely important, especially when the beam exposed to bending. Therefore, we always focus on the axial and bending energy system, but also we saw some example related to energy comes from the shear and torsion. So let's start with the axial load. Maybe you remember in chapter 1 or 2, I can't remember, in strength of material, chapter 2, sigma is equal to, for due to axial load, P time divided by A, but I want to use an N notation instead of the force, the normal force divided by A. It's a typical formulation. So So also we know the epsilon is equal to sigma divided by E. So if I want to, you remember the 1/2 sigma time, also I can use the N/A instead of sigma, so epsilon becomes N divided by EA. If I want to use the internal energy formulation, U is equal to integration 1/2 sigma times epsilon. So if I want to include in the formulation 1/2 N A times N EA, so integration becomes, also dy, this is volume integration, I forgot to write the dy, so 1/2 N square EI square dV. So from 0 to this is volume integration, So how we can measure the volume integration? First of all, if I have a constant cross-section shape like in this figure, I can write also N, if the N is constant, Also, modulus of elasticity is the, the constant. Also, area is constant, so I can move these three terms out of integration. So our integration becomes, is constant. If I think this term is constant, so our integration becomes like this: 1 over 2 n square ei square. So integration dv. So this is equal to, I can say, integration of dv is become to volume. Volume of 2 our body. So I can, if our cross section is constant, I can say a times f, area times length. So you can see this term is disappear. So I obtain the internal energy ui becomes n square L ei is 1 over divided by 2, like this formulation. For bending, our relationship a little bit different. Also, I want to make a little bit proof in here. I want to again open my camera. Do you remember sigma is equal to m divided by moment of inertia times y? Also, epsilon is equal to, again, similar. Therefore, I want to write to m ei times y in here. So our internal energy ui is equal to 1 over 2 sigma epsilon dy is equal to integration 1 over 2. I want to write these terms: m square e times I square times y square dv, like this. And maybe some of you said, Hocam, m is constant, we can take advantage of integration. M is not constant, therefore I cannot write m. But if I can say is the I is constant and also E is constant, okay, I can move these terms out of integration. So UE is equal to 1 over 2 E I square integration. I want to, volume integration, I want to divide with 2 area integration. I'm sorry, I'm not sure. Yes, out of integration. Also, moment is constant during constant in, okay, sorry. I can change different techniques, sorry. So I and moment terms are constant in same cross section area. So in same area is constant. Therefore, for example, if beam like this, okay, we have a moment. This moment is constant, but if with different length, moment can vary. Also, moment of inertia can vary if our shape cross section shape is changed. Therefore, I want to divide to integration 2 parts like this. First term is from 0 to L dx, like length change. Also, I want to divide to area integration. Also, I say to if this term is constant, I can move these terms out of integration. 1 over 2 m square e I square. So inside of the parentheses, we have the area integration. Sorry, I want to move out of like this. Dx a little bit in here. Y square dA, like I want to put in parentheses, this is area integration, times dx, like this. So, you know, y squared dA is the moment of inertia. It's equal to I. Therefore, in I times I divided by I squared, I can obtain Ui is equal to, from 0 to L, 1 over 2 m EI d, sorry, m squared EI dx. Sorry, this is the internal moment energy. Also, you can see in here. Also, for transfers here, I don't want to use my whiteboard. I can use this slide is okay because I don't want to lose time for proof. Also, you don't need to learn the proof of these internal energy, but just I want to show how we can obtain this by using the similar techniques. You know, for strain energy or transfers here, you can remember we used the tau times gamma divided by 2. Therefore, I can write VQIT for tau like this. Also, I can use gamma is equal to tau divided by G, so VQGIT. If I include in here total internal energy due to transfer shear from the transfer shear by using this formula, 1 over 2G times in parentheses VQ divided by IT square. So, you know, dV is equal to A dA times dx. So, similarly, from bending, I want to divide the parentheses in, you know, area integration and length integration like this. Also, I want to say similarly to VRI terms. You know, V is the shear force and moment of inertia constant in same cross section. Therefore, I can move first integration term out of integration. So V squared GI squared is equal to, in area integration, Q divided by T squared dA. So I cannot say what is the meaning of this term. Yes, this is a little bit difficult, but I can say there is no specific answer. We can say like this term as a form factor. Okay, so I want to simplify as a fs, and under that, if I say this term as a fs, our formulation ui is equal to, from 0 to L, fs v squared 2ga. So fs is why is important, because fs is also, you can understand from the name, it's depends on the shape of the cross section. Therefore, there is some kind of specific numbers for cross section. For example, in f is equal to 6 over 5 for rectangle, f is equal to, so not rectangle, is 9 for circle. This comes from the copy and paste. Actually, sorry, circle. Also, f is equal to I divided by I web for I beams. Sorry, like this. I need to fix these things, but I have a little bit problem. Okay, I got it. Okay, we can continue. So fs is not big deal for us if we use like these kind of shapes in order to compute strain energy from transverse shear. Okay, the last term is the strain energy due to torsion. We will use the same energy, you know, from torsion to shear stress can occur. Therefore, we will use the tau gamma divided by 2. So instead of tau, you remember from the chapter 5, the torsion times rho divided times j. Rho is the radius. So also gamma is equal to tau divided by j. Also, if I included instead of if I write these terms for tau, I obtain these terms. And if I substitute these two terms in the UI formulation, we obtain like these complicated terms. Also, similarly for bending and transfer shear, if I want to divide the dVs dA times dx, so integration becomes like this. Also, tau and g are constant in cross-section A, therefore I can move these tau, g, and j terms out of integration. In integration, only rho remaining, and rho squared dA, maybe you remember or not, I don't know from the static course, but this is equal to polar moment of inertia. Therefore, I can write the j instead of this term. After writing j, you know, j is 1 power of j is disappear, and our formulation is t squared 2g j dx. So you don't need to memorize this formulation. Also, you know, in exam, final exam, I think can be to we will apply using like to LMS system, online system. Therefore, you can reach the sources. Also, you can see the formulations. Therefore, you don't just only, I want that you please understand the main theory of the energy principle, just force times displacements, nothing more, okay? Maybe you can see the different complicated functions, okay? Don't stack this, okay? Just only concentrate to what is the general meaning of the energy. For me is enough, because, you know, just only, you know, which type of internal effect occur. Okay, look at the formulation and apply the formulation, get the result, nothing more. Okay, let's start with the example 14.1. We have a two type of bolts available, bolt A and B, shown in this figure. In first figure, its bolt length is little bit, and in first bolt, you know, it's, don't think about the after this. I can just only we are concentrating from the 56 millimeter part. Okay, this part is not important, therefore. Okay, and in bolt A we have a first part, you know, have a diameter is 20 millimeter, and second part, okay, is diameter is about from 6 millimeter part, is the diameter is 16 millimeter. For bolt B, we have whole part as same diameter, which is equal to 18 millimeter. The question asks that please calculate strain energy of this term, the maximum strain energy observed from the these bolts. You know, it's also we are working on the linear case, therefore the maximum normal force can be equal to the yield stress, which is equal to 310 megapascal. Also, modulus of elasticity of steel is given. This is not megapascal. This should be 210 gigapascal. So, first of all, which type of effect can occur? Now, this is the bolt. Bolt can resist just only to tension or compression. In other words, the axial load. So, yeah, concentrate by using force. So, in the formulation, N square L divided by EA. So, we know the L, we know the I, we know the E, but we don't know the N. First of all, we need to find the N values. So, you know, to limit force, the maximum force should be equal to, I want to write like this, how we can find the maximum force. So, how we can find the N max? You know, N max is equal to sigma maximum times to area. So, What is the sigma max? I said it should be can resist the yield modulus, therefore area. So which area is the smallest area? Because in both A we have two area. Which one is the critical? The smallest I is critical. Therefore, for both A, we have two area. The first part and area 1 is equal to P times, what is the diameter? 20. 20 squared divided by 4. And where to x is equal to from 0 to x 50 millimeter. In second part we have, in second part we have an A2 is equal to P times 18 squared times 4, and in here we can use a 0, x is equal to, start from 2, 50 x 56. So what is the n max? Which one is the smaller? A2. Therefore, I want to write for both A to n maximum is equal to, what is the sigma maximum? 310 megapascal, sigma y, and also area, I want to use the area too, P times 18 squared divided by 4. I want to look at the computing result is equal to, you can see 78,886 Newton. Okay, you know, we are working with the Newton millimeter, so principal Newton millimeter, that becomes to megapascal. I don't want any unit conversion in here. Okay, so I can compute the n, and after that I can use the part. So what is our formation? You remember that ui is equal to n squared times ei times f. So, but in here we have two parts. Therefore, I have to use the different sections. Therefore, and first one, n a1 l1 times n squared divided by ei2 l2. So if I want to continue, you know, n is equal to 7,886 divided by E is equal to, you remember that, to 210 gigapascal. I need to convert to the megapascal. Therefore, 210,000 times area 1 is given, P times 20 squared divided by 4, and times L1 is equal to 50 plus, again, I'm sorry, this should be square, again 786 square divided by 20,000, this should be one in here, one more 0, times P 18 square divided by 4 times 6. Okay, by using this general formulation, I obtain U is equal to, look at the solution for both A, and where is it, both A is not computed in here? Yeah, in here, sorry, I'm passing so quickly, and we obtained 2.708 joule as written in here. For both B, you know, we have only one area. Therefore, its area formulation is like this. So we don't need to compute to what is the smallest and biggest. Therefore, N max is equal to directly equal to area 2. Therefore, we have same normal force value, maximum force value. So in other words, both bolts can carry same axial force, but energies can be different. Maybe you have a think about which one can have more strain energy formulation. Now we will see. So I want to change the formulation. I don't need to divide the internal energy to two parts. I have just only one part is okay. Therefore, I have to write to n square EIL, and I want to write to this term instead of 8n, sorry, and 210,000 times P 18 squared divided by 4 times 86. And after that, we obtain the internal energy for both B is equal to, you can see, 3.26 joule. Maybe most of you think that the bolt A can resist more than energy than bolt B, but you can see, bolt B can carry more energy because, the diameter is low, can displace more, therefore can carry more energy. So sometimes, most of you think that if our structure can have more rigid, can absorb to more energy due to earthquake loads. But also this is a good thing that sometimes we need to decrease the rigidity of the structure in order to can absorb more earthquake loads. Therefore, always, think about this formulation is important. Increasing the rigidity, increasing the size of the structures cannot be sometimes be so good solution to absorb more energy. In order to absorb more energy, sometimes we need to decrease the rigidity. Sometimes we need to decrease the size of our structures. Can be maybe for more effective. Okay, let's continue with the chapter 14.2. Now we have a we have a like beam, and on the beam we have a distributed load omega. This value is not given. We will find these values in non-numerically symbolic terms and by the omega formulation. So there is a determined elastic strain energy due to bending. Also shear force can be applied this energy, but just only due to bending and I is constant during the beam. Therefore, we will use bending formulation in here. And I is constant. Therefore, M, we will use the bending formulation in here. M squared 2 EI. So first of all, I want to write the formulation. Sorry, I have enough space in here. Maybe I can use this part. Okay. So I said UI is equal to integrate mx squared divided by EI. Sorry, sometimes I forget formulation in here. Where is the formulation? Yes, 2EI dx. Sorry, 2EI dx. So AI is constant, so we just only find the moment with respect to the omega value. We have our shape like this, and first end in free, second end is a fixed support. We have a shape like this. Sorry, I don't want to use the blue pen. Also, like this. We have a support reaction in here. Okay. Also distributed load omega in here. Okay. I want to origin in this point. I want to take a cross section. X, and I want to take this part, take a cross section. After taking a cross section, is omega. This length is x. This sum of these forces is omega x, which is also x divided by 2. Also internal moment in here. There is no support reaction on the left side. So omega x is equal to minus omega x times x over 2. This is equal to minus omega x squared over 2. So I want to write in the formulation ui is equal to 1 over 2 minus omega x squared over 2 square ei dx. After that, 1 over 4, 1 over 4, 1 over 8 integral omega x to the power 4 divided by ei dx, sorry, omega squared 4. So if I want to compute 1 over 8, is also omega is constant, omega squared. What about the integration of x to the power 4 is equal to x to the power 5 divided by 5. Also integration from 0 to L, so you put this. So 0 to L, if I put this, 1 over 8 from omega square L is 5 times 5. 8 multiplied by 5 is equal to 40. And we obtain omega square L to the power 5 divided by 40. Like this. This is our result. I hope I calculate correct. Let me control this. Yes, we have same value. Also, chapter 14.3, we have a same loading system. Now, strange energy calculated from strain energy from transfer shear. Therefore, we will use the same bending, same loading system, just only computing from the strain energy formulation. Let me control our formulation due to transfer shear is equal to Fs times V squared 2Ga. I want to update it to my formulation. V squared Fs 2Ga dx. Sorry, I forgot to open my camera. I write this formulation in here. So I want to go back to the question. Also, we are wondering that what is the meaning of Fs. F, we have a rectangular shape. On rectangular shape, you remember the F is equal to rectangular shape is 6.6 divided by 5. Therefore, in UI in this combination, 6 divided by 10 integration V squared Ga. So just only we need to find the shear force. I take a similar cross section and shear force direction like this, down direction, and omega x becomes, Vx becomes exactly in minus Wx. So I want to write this formulation in our general formulation. So ui we obtain in here. Ui is equal to 6 divided by 10 integration minus omega x square GA like this, x. So omega is the constant, therefore we can move out of integration. 6 omega square divided by 10, so x square inside 10 GA. So x to power divided by 3 from 0 to L. Okay, if I put this term, we can see ui is equal to 6 omega squared 10 GA times L cubed divided by 3. You know, this term is 215 omega square L cubed divided by 5 GA. This is the UI formulation, sorry, like this formulation. Let me control our solution. Yes, also you can see y square L cubed 5 GA. This is the answer. The last combination is the example 14.4. We have a shaft in here. We have two torsion in here. I can't draw 3D shape. I want to explain the formation, explain this free body bias in 2D, two-dimensional shape. Sorry for bad drawing for the beginning. Sorry for that. Okay, we have a. I want to draw a free body diagram like this. We have a shaft like this. At the beginning of the shaft, we have a 40 is counterclockwise. It's up to me, and I can say, no, I misdraw like this direction. Right, this direction is positive, okay. The x direction is positive, therefore the torque is the positive and positive torque. Now, using the right rule, you know, as positive 40, okay. And this length is how many? Written in here, 750 millimeter. Okay. After that, we have a reverse minus 55 and torque, and also this length is 300 millimeter. So we have two parts. Let me control the general formulation. Due to torsion is equal to ui is equal to, from 0 to L is equal to t square times 2gl dx. So this is the general formulation, but in here we have different parts. In, you know, t is different, you know, two areas. The first area, the second area. Therefore, I have to divide the integral. For example, this is a starting point, okay, from 0 to 40, okay. T is equal to, in here, I can say later, okay, and also, so not 40, I'm sorry, where is it comes from? So this is the value is 40, 750 in here, also from 750 to 1010, okay. Also t square 2gl dx. So I want to use the subscript in here, t1 and t2 in here. What is the t1? T1 is okay. I think that you can easily get. I take a cross section and here, and t1 is also should be right. T1, and this is 40, so t1 is equal to positive 40, okay. But also this cross section, first part, and also I want to take a second cross section. This is part 1 and part 2, and this is 40, this is 55, and this is the T2. And sorry, I badly draw, I forgot to draw. T1 is 40, and I want to take a cross section 2 in here, and after that T2 is, you can see, minus 15 in here. So T1 is 40, T1 is minus 15. Don't write 55, because if I want to take a cross section, I want to add this. Don't start with the right side, because this right side is a support in here. Total support is minus 15 in here. Okay, if I take this, start from take the right side, don't forget to put the reaction torsion force in here. Okay, I want to erase this part because I already calculated T1 and T2 in here. So from 0 to 750 divided by T1 is equal, I said, 4 square 2 times, what is the value of the G? Where is it, G? G is 7.5 gigapascal. I need to convert to the megapascal. 7,000 times, what is the value of the G? Sorry, this is not G, J. I write to like L, sorry, this is not J, this should be J in here. Sorry. Okay, I might make hand computation in here. Okay, what is the J? J is the polar moment of inertia. This is the hollow section. I don't want to, hollow section. We have like this. As thickness is given, what is the meaning of thickness and 15 millimeter, and what is the diameter? Diameter is the 80 millimeter. Therefore, P times R square over 4 modulus of elasticity. So, but we have two shape. Is the hollow? How we can calculate the J in hollow section? First of all, we have the whole array is solid. Then we subtract from the hollow part. In first case, when the whole section is solid, its J becomes the P times. And what is the R? R is 40. 40 to power 4 divided by, sorry, this should be in 4. I forgot to write in here. 4 minus. Now I will subtract from the hollow. Hollow part is, you can see, thickness is the 15 millimeter. To thickness, as it should becomes the 15 plus 15, 30 millimeters. Therefore, the whole diameter becomes to 80 minus 50, sorry, 30, 50 millimeters. Therefore, I can write P times 25 squared divided by 4. I hope book calculated for us. Actually calculated in here. They convert to the meter, but I want to use the millimeter. Okay, 16.3. Okay, and 10 to power 6 millimeter over 4. Okay, where is it? My system in here, millimeter over 4. Okay, this is the also Newton meter. Also, I want to convert to the Newton millimeter. Therefore, I need to little bit changes in here. It's 40,000 square times 36.3 10 to power 6. Like it's square, like this. This is the first part. Plus, I want to go back to the second part, and T2 is equal to from 750 to 1050, minus 5,000 square divided by 2 times 7 or 5,000 times 36.3 3 10 to the power 6, like this. Then after that, we obtain the real value to 0.233 joule. Here is the result. This is not doing here. Okay. And you can check the results, okay? I don't trust the book result, but I didn't control it. Maybe you can check result and control it. I'm working in the system a little bit differently, Newton millimeter, okay? Therefore, I convert to the sum of the values from meter to millimeter, okay? Book works with the Newton meter in here. Okay, now I hope you'll learn to do what is the meaning of the strain energy and how we can calculate the strain energy. Now we can pass to the energy conservation of energy. I say the conservation energy is equal to UI. So conservation energy principle is equal to U external energy is equal to internal energy. I say the 1/2 P times delta is equal to internal energy. So we know how we know to compute the internal energy. So we know the external force. Now we can compute to the delta. So by using conservation of energy principle, we can compute any. So we can compute the displacement of the structure. Okay, let's continue. So what is the meaning for conservation of energy? I said the UE is U time. Now, so for trans, 1/2 P time delta, like this, for example, if I have like a trans and we put an external load P in here and we want to measure delta in this point, okay, how we can calculate this? By using this formulation. And what about for beam? Also, we have an external load anywhere of the beam and we want to measure delta displacement in here. How we can calculate? We either by using 1/2 P times delta is equal to 1/0 m square EI dx. Similarly, but you don't know this, always we are talking about the P times delta, but sometimes we need to measure the slope delta. How we can measure the delta and slope? Now we use to have any moment and we want to measure the slope, okay? 1/2 m times delta, again, it's equal to m squared 2EI energy for the bending moment. Maybe you can see some of you wondering that, Hocam, what about the shear force? How we can compute the shear force in here? Mostly for bending, we combine with the shear force and bending force, but generally for bending procedure and bending criteria, the shear energy, if I want to compare with the bending energy and shear strain energy, bending energy is much more higher than the shear strain energy. Therefore, we always eliminate the shear strain energy. Also, torsion energy is extremely small if we want to compare with the bending energy. Therefore, we are focusing on just on bending and axial load. Also, we don't combine bending and axial load. We have to solve these terminology differently, separately. Okay. Let's start with example 14.5. In this example, we have a 3-bar system. Okay, there's some kind of external force, 20 kilonewton, sorry. If the cross-sectional area is 100 millimeter, determine the horizontal displacement on the B. Now, what is the horizontal displacement point B? Also, modulus of elasticity is given 2 gigapascal. Again, I want to work with Newton millimeter and megapascal terminology. And first of all, I want to, how we can find? First of all, we need to find the axial forces occurred on the truss members. How we can use? Now, this is a statically determined system. So by using statically determined system, we can use the method of joints, for example. By using method of joints, we can use all member forces. Let's start with the point B. Now we have point B. I take the point B. We have two forces on point B. With three forces, two internal forces. For example, in here we have a FAB. We have in here 20 kilonewton, and we have like the FBC 60 degree in here. Okay. Now sigma Fx is equal to 0. So you can see FBC is equal to minus 20 divided by sine 60 degrees, FBC, sorry. And after that, I think I have calculated this. Where is it? Minus 23.094. Okay. Also, sigma Fy is equal to 0. FAB, I want to take positive, minus 23.094 times cosine 60 is equal to 0. So FAB is equal to half of this, 11.547 kilonewton. Also, I want to continue to point C. Where is it? Yes, point C in here. On point C. This is compression. Therefore, I will need to change the direction like this. On point C, FBC is equal to 23.094. Support reaction G. Also, we have a force FAC. We can see sigma Fx is equal to, also this degree is 30 degrees. Sigma Fx is equal to 0. FAC is equal to 0.904 times cosine 30. I think this is equal to even 20 kilonewton. Sorry, I'm using this one. Okay, sigma Fx is equal to 0. Fa is equal to, that's to x part of 23.09 by using this. Okay, you have already experience about the method of change. Therefore, I am solving a little bit quickly. So we have three members. Therefore, we have three internal strain energy observed by the member. Therefore, I want to use the table in here. Where is it, the table? Oh, we don't need to use table, but we can use it. Why we are using this? It's up to us. I want to use a table in here differently. There is no my Excel. Just member AB, BC, AC. I want to go back to the slide. What about the AB is this term? Copy. I made a mistake. I think that. Where is the BC? BC is equal to minus times 2, and this is the AC is equal to 20. I remember that. Yes, minus 20. I don't think so. It should be a minus. Actually, I made a mistake. Yeah, this should be minus. Sorry, I made a mistake. No, I think this should be positive, not be minus. Something I miscalculated. I did that. This should be positive. Okay, let's continue. And this is the normal force. You know, our formulation is the modulus of, I want to convert it to this term is the Newton. Therefore, I want to convert to the Newton terms and copy and numerically like this one. This is normal force. And modulus of elasticity is given in the question. What is the modulus of elasticity? Modulus of elasticity 2 gigapascal. I want to convert it to megapascal. 200 gigapascal. Yep. So I want to convert it to of elasticity in here. Also, L is needed for AB element. We have a 1 meter length. Therefore, I want to like L is equal to 1000. For BC, we have 2 meter. BC, therefore, I want to like 2000. So what about for AC? AC is I can find is 2000 fine cosine of 30. Therefore, I can use the formulation. This one times cosine 30 like this. Oh, I think they are using two different terminology. Just P divided by, yeah, like this. Okay. This is using the radian angle, but therefore I will need to convert to the I'm sorry, yes, I want to convert. This is this system working with radian angle, therefore I need to convert from degree to radian. I'm using this one. Okay, and L and E are okay. You remember our formulation is the n square L times EA. Also A is missing. In A also A is given 100. Also I need to write. Okay, this is 100. Okay, so and UI is equal to, remember that n square. Okay, sorry, E times A divided by times L, like this. N square divided by EI multiplied by L. After that, I'm sorry, like this. And if I want to, sum these values, we obtain the total internal energy and total UI. This is the formulation. This is our result. Compare it to our book result. I hope this one is correct. No, okay, this is correct. So, in the question, you remember that. So, total UI is equal to 4.60 joule. Okay, so this is equal to 1/2 P times delta. So what is the P? The question is given. P is due 20 kilonewton. Therefore, I can write 1/2 20,000 delta is equal to 9464.60. And after that, you can see delta is equal to 94.60. We are working with the millimeter, therefore, displacement becomes the millimeter like this. Okay, now we'll continue a new subchapter, chapter 17.3, Principle of the Virtual Work. Actually, in previous chapter, if you want to, in the examples, is a specific example. Maybe you realize or not. For example, in last example, in order to find the displacement on point B, also the external load is also in the same location. If we, for example, if we're wondering to what about vertical displacement on point C, unfortunately, we cannot use the conservation of energy principle. In order to use the conservation of principle, both energy and point load should be in same location. Therefore, in different location, we have a trouble. Okay, we have to use a different principle, and on this we will use the principle of virtual work. It's also based on the conservation of principle, but the methodology is a little bit different because you can know what is the meaning of the virtual, you know, we know that that is not real, therefore the work is not real. So in order to be some terms, we need to want to be virtualized. I don't want to go in the proof, just I want to go into location. In here, we want to displacement is virtualized. Therefore, in the when the force is virtualized. After the force is in the virtualized, and we have a different strain energy doing this force. So it's a virtualized. Therefore, in the point for example 1. If we take the force as a 1 in virtual force, and we obtain the real displacement by using this. Okay, I don't want to go into proof, just I want to go into location. You know, in strain energy formulation, we know the axial load, shear, bending, and torsional moment, like n squared, v squared, m squared, like this formulation. Okay, when we are using the virtual work, we divide the normal force into two separate parts. The first separate force is the normal force coming from the real load. Also, we use the small n in this formulation. For example, these normal force come from the virtual load combination. So, in our example, we have two type of loading types. First loading type, real loading type. By using these real loading types, we can calculate the normal force, shear force, moment of torsion, which type of two values needed, or which type of energy occurred in the system. Then we will put the, for example, which type of displacement needed. Okay, we will use the virtual loading in this. For example, normal loads, we will use a small and we will put to. I think that it is not easy to explain on the programming. I think I can explain in my camera. For example, if I like thrust system like this, okay, and we have a different loading types, for example, 50 and 60 kilonewton, and point A and pin support, point C is a roller support. For example, this is the real loading type, and question wants the virtual loading and also point C, and they want the horizontal displacement in here. Okay, in order to for virtual work principle, we have two loading types. First real loading type is the real loading. Second loading is the virtual loading. For virtual loading, okay, we eliminate these forces. Okay, we don't need to take into account these forces. We put a unit force, like just one force, on which direction, in delta direction, in horizontal, we put this force, and loading type is second loading type is the virtual loading. So we have, and for real loading, we can calculate to NAB, NAC, and NBC. In virtual loading also we calculate to small NAB, NAC, and BC. So we compute these six values and apply to our formulation in here. We obtain the real force. Also in shear force, we have a small v. This comes from the shear force obtained from the virtual loading. Also we have a bending moment, small m, also is obtained from the virtual loading. So in our system, okay, if the displacement is needed, we put a unit force, okay. If the rotation is needed, we put to unit rotation in our unit moment, unit moment in this location. So if in our in virtual displacement, in virtual work method, in the question, when the displacement is needed, we put a unit force for virtual loading type, okay. For if in the question slope is needed of the beam, we put a unit moment on the beam for virtual loading. So this is a type of the trusses in truss system. I said also we have a different type of trusses. We will use a summation, similarly energy conservation method. Okay, and also on beam we have one element. Therefore we will use the integration, and we obtain the solution. Okay, it's the best way to understand the virtual math method. You're using the example. We have how many members? 1, 2, 3, 4. 4 bar member. Okay. In a member, we have a cross-sectional area is given, is 400 millimeters square. Also, a modulus of elasticity is given, 200 gigapascal. Okay. The question wants that the vertical point on point C, truss shown in figure and cross-section, find to determine the vertical displacement on point C. So we have a two type of loading, I said. First of all, I want to draw the rail loading. And I want to draw a structure. I want to use the camera in here, rail loading. I want to draw a structure. Here is the 100 kilonewton in here. This is rail loading. Okay. Also in here, both ends in, I think that pin support, I don't care about to support direction, but I can use it. AX, AY, sorry, AY, AX, and also DY, DX. Okay, by method of joints, I can find to I don't want to go in detail. Okay, you know what's the meaning of how you can use the method of joining truss. Okay, by using this loading system, we can find to force AB, FBC, FCD, and FAC. In order to make a summation, I just only want to find just only two loads, FAB and FBC. Okay, remaining structural members, remaining forces of the structural members, you can calculate by your previous knowledge. Okay, just only I want to work with point B. On point B, I'm drawing the free body diagram, and sorry, 100 kilonewton in here, two forces in here, FAB, and one force in here, just also CAD, FBC. This angle is 45 degrees. Okay. Now sigma Fx is equal to 0, so not Fx. First of all, I want to start with the Fy. Okay, FBC is equal to positive 100 square root 2. I'm sorry, I'm a little bit going fast, but if you want, I can do it for you in detail. FBC times sine 45 degree minus 100 is equal to 0. You can see FBC is equal to 100 divided by sine 45 degree. You know, sine 45 is 1 over square root. Therefore, FBZ is equal to 100 and square root 2. After that, sigma Fx is equal to 0. You can see FAB is equal to minus FBC times cosine 45. And after that, I found FAB is equal to minus 100 kilonewton. This is a minus, meaning that the compression, positive meaning that the tension, because at the beginning I assume that both internal forces of the members are tension. Okay, also these remaining forces are already calculated. Also, it's available in the result. Okay. After that, you can see, you know, AB is 1x minus 100 and BC is 141.4 and AC is 141.4 and CD is 300. So we obtained the capital N. Also, I need to change the small n here. This one is much better. Okay. Now I want to pass to the second type of loading. Second type of loading is the unit load. How we can use? You can see, I want to delete these parts. Okay. And for unit load case, okay, I delete to all external loads, virtual loading case. Okay. I put the question needs that to vertical displacement on point C. Therefore, I put a, sorry, where is my camera? In here. So vertical displacement on point C. Therefore, I need to put a vertical force, but value is unit force. Okay. Therefore, the value is 1, direction is vertical. It doesn't matter right to left or left to right, because that means that I assume that the displacement, the C, point C going to this direction. If you think C is going to that direction, okay, you can use a different direction. It ups to, you know our assumption. If I assume, if I obtain the delta is positive, that's meaning that my displacement is from left to right. If the delta is minus, my point C going from the right to left. Okay, so I put a point load in here, and I can start. You know, on point B, you can see point B, there's no force in here, and force is 0. Therefore, there's a FAB and FBC. In here, no forces in here. Therefore, FBC is equal to 0. FAB is equal to 0 on point B. I want to pass to the point C. On point C, you can see, and there's a 2 pi flow loading in here, and FDC, FAC. I don't need to draw to FBC because, you know, F value of the force BC is equal to 0. Just on, I want to put the unit force 1 in here. You can see there's some kind of angle 45 degree. Sigma Fy is equal to 0. You can see FAC is equal to also 0. And actually, sigma Fx is equal to 0 from, I can obtain that FDC is equal to 1. Therefore, just only we have one force, then FDC, and which is equal to tension. Sorry, you know, Fx is equal to 0. Therefore, FDC, not O, this is D, DC becomes 0. So we have 4 members, just only one member take load, which is equal to member DC, which is the member DC. Okay, so I also apply our table, my forces in here. You can see 0, 0, I'm not sure AC is not minus 1.441. Just let me check if I made a mistake or not. I'm sorry. I'm terribly sorry. Actually, I recognize that too. Force is not horizontal, vertical. Therefore,